is equal to $3 per foot for Y length,
it would be great if you could get out a piece of
plus
paper so
$7 a foot for X length,
we're going through the problem. It makes a
and
lot
another $3 a foot for the other side Y length. So we've got 6Ys plus 7X is equal to our cost. And again, we have too many variables. We know we want to be able to take a derivative. So we'll come back over to this equation, solve for y. Y equals 2,000 over x. And we'll use that up here, that the cost is equal to 6 times 2,000 over x plus 7x, or the cost is equal to 12,000 over x plus 7x. Well, if I need to take a derivative, I don't really like having that x in the denominator, so I'm going to make that 12,000 x to the negative 1 plus 7x, so that when I go to take the derivative, I can do that more easily and have this negative 12,000 x to the minus 2 plus 7. Or if you prefer, we can do 7 minus 12,000 x to the minus 2. And from there, we're going to set that equal to 0. And we have 7 minus, let's do that as 12,000 over x squared equals 0, or 7 equals 12,000 over x squared. 7x squared equals 12,000. So x squared equals 12,000 over 7. Take the square root of each side. We don't need to consider the negative. So the square root of 12,000 over 7, which is approximately 41.4. As always, we want to check our answer and make sure that if we're looking for a minimum, that we're getting a minimum. So these are our x values. Our key value here is this 41.4. If I look back at my equation as I have it in the box, it might be easier to look at it as c prime equals 7 minus 12,000 over x squared. When I'm looking at it in this form, I can say, well, I can't plug in a 0 for x because that's undefined, but I could plug in a 1, and then I have 7 minus 12,000. So to the left of our key value is negative. If I plug in something bigger, let's think about 100, that's going to now be a positive value. So that's decreasing, that's increasing, that's a minimum, and that's what we wanted. So our x value is equal to 41.4. Our y value, y equals 2,000 over x. Y equals 2,000 over 41.4 gives us 48.3 feet. And those are both approximate. Now we want to know what is our cost. Well, we'll come back to our cost equation. The cost is going to be the 41.4 feet times $7. And 2 of those 48.3 feet times $3 gives us this, you'll find kind of curious, 289.80 plus 289.80 gives us a total cost of $579.60. And that is our minimum cost. Hope that helps.
Times 18 minus 2 2-inch edges times a height of 2, which is 560 cubic inches. And lastly, what's the volume of the box if a 5-inch tab is cut? Well, I'd have the volume equals 24 minus 2 5s, 18 minus 2 5s, times 5 gives me 560 cubic inches. Okay, so you knew what was coming here. Find the size square tab that will produce the box of the greatest possible volume. So we've got another max problem. If we want to maximize volume, what kind of an equation do we need? We need a volume equation. Okay, so I've already done this up above. Suggestion, call the side of the square x and express the dimensions of the box in terms of x. So we've done that up above. Find the formula for the volume of a box in terms of x, and then use calculus to find the maximum value. Okay, so our volume we know is length times width times height. So our volume in this case is the 24 minus 2x. My width is 18 minus 2x, and my height is the x. Because again, remember, I folded up the height of this square is x, and my length is the entire 24 minus an x and minus another x. And my width is 18 minus an x and minus another x. Tidying that up, multiplying out these binomials using distributive, I've got 432 minus 48x minus 36x plus 4x squared, and I'm still going to need to multiply that by another x. So tidying that up, adding these two together and distributing in that x, I have my volume is equal to 432x minus 84x squared plus 4x cubed. So the next move, now that I've got a nice tidy equation, is to take the derivative. So my derivative dv dx is equal to 432 minus 168x plus 12x squared. I'm going to set that equal to 0, and I'm also going to rearrange it so it looks like a quadratic equation, a comfortable quadratic equation. So 0 equals 12x squared minus 168x plus 432. And factoring or using our quad program, we come out with x equals 10.0 or x equals 3.4. And I'm not going to do this in the context of the problem yet. I'm just going to go ahead mechanically, and I'm going to look at my sign chart. If I've got 3.4 and 10, this is a quadratic equation. And here's my quadratic equation right here. Quadratic equation, lead coefficient is positive, so I know that it is a parabola that opens up. So I've got positive values, 0, negative values, 0, positive values. So uphill, downhill, uphill. I have a max and I have a min. So my maximum volume is when x equals 3.4. So my max volume, x equals 3.4. A minimum would be at 10. We'll come back and look at that in a second for why that is. And if I want to know the volume, I'm going to have the volume is 24 minus 2 times 3.4, because I'm cutting a square out on each side, and 10 minus 2 times 3.4 times 3.4 gives me a volume of 654.98 cubic inches. Well, let's go back and just look at this 10 for a second. If x equals 10, if I cut off 10 inches, well, I don't have 10 inches to cut off. I'd be cutting off a total of 20 inches, and the side of my box is only 18 inches. So certainly I can't cut off 10 inches. That just doesn't make sense. X can't equal 10. So we want to consider what is even allowable for x. So our x values need to be something bigger than 0, because if you don't cut off something, this is working here, if I don't cut off something, then I don't have any box at all. And the largest that I could cut off is half of that width, which is 9, and so I'm going to cut off something slightly less than that. So I'm going to say that x has to be greater than 0 and less than 9. And I apologize that this, for some reason, is looking funky. X is greater than 0 and less than 9. And I wanted to give you some nice notation that my domain is all x's such that x is greater than 0, less than 9.